We continue on talking about using property tables. Let's talk about continuing on our discussion of determining the phase, which again, we said that's back here, a sub-step within step three, but this is really kind of the most important one we want to master because that's what stands in the way of us finding the other properties we need to solve whatever problem we're working on. So if we would continue on looking at determining the phase. So important thing here, given pressure and temperature, right? So given pressure and temperature. So we saw in the previous problem, given pressure and specific volume, this is another scenario. A very common scenario is given pressure and temperature. So if that's what we have here, I don't know why my pen didn't come out. Given pressure and temperature, if the temperature is greater than the saturated temperature, essentially the boiling temperature, at the given pressure, then you have a superheated vapor. So again, remember, given pressure and temperature, our diagrams look like this, and I just have an arbitrary curve out here. And what we're saying is that at the given pressure, you can go look up your saturated temperature. That's essentially your boiling temperature at that given pressure. And if you have a temperature that's higher than your saturated temperature, that puts you out here in the superheated vapor region. That's to the left of the curve. And again, the curve, we're looking at the edge of the saturated dome when we see this curve here on the PT diagram. So this is really the saturated dome. We're just looking at the edge of it. And over here to the left, if I have a temperature that is less than my saturated temperature, that puts me over here in the compressed liquid region. Right over here in the compressed liquid region. Now, a way you can kind of think about that is like think about water at 1 atmosphere. So if I've got water at 1 atmosphere, say as my given pressure here. So if I've got water at 1 atmosphere, well, the saturated temperature, the boiling temperature is going to be 100 degrees C or 212 Fahrenheit. So if I've got 1 atmosphere and I've got, say, 300 Celsius or Celsius or Fahrenheit for that matter, 300 at 1 atmosphere, in both cases, that puts me beyond the saturated temperature, puts me in the superheated vapor region. Same thing on the other side. If I've got, say, 60 Celsius or even 60 Fahrenheit, that puts me less than the saturated temperature. That puts me over here in compressed liquid. And so that's what it looks like graphically. Let's put this to work. Let's look at an R134 problem. So I've got a rigid vessel filled with, example here, givens. I'm going to write it larger than I normally would, so you can kind of see what I'm writing down here. We've got R134A, refrigerant 134A. They've given me a mass here of 2 kilograms. They've given me a pressure of 900 kilopascals, kPa if you like, kilopascals. And then a temperature of 80 degrees C. 80 degrees Celsius. And they want us to find the total volume of the tank, and they want us to find the internal energy. Now, they've not specified if they want little u, which we would pull right off the table, or if they want capital U, the total internal energy. Well, it's not hard to give them either one, so we'll give them both. Okay. Okay. So what do we do with that? Well, we're in a situation where I'm trying to find an unknown property. So I'm trying to find an unknown property. So we go through my checklist that I've got up above. Hopefully you've got yours handy. The first one is identify your substance. I've got R134A. So I have property tables for R134A. They work the same way as the water tables do. And these are metric units. The metric units work the same way the English tables do. So we're going to use R134A tables. I need to identify known properties. I've got pressure and temperature. So given pressure and temperature, that's going to go on to step three. How I determine my phase is going to take a specific form given a pressure and temperature combination. And then the last step is write down the other known properties or needed properties that I need. Well, I need total volume. I'm looking for total volume, which you won't find total volume in your tables, right? If I look at, here's a table for R134A metric units, and I know you can't quite see it unless I zoom in, but it gives me specific volume, not total volume. I get lowercase v's. But the problem specifically wants me to find the total volume. So how do I do that? Well, the tables are written in what's called intensive properties. They're the scaled version, they're per unit mass. So all I need to know is how much mass I have, and I can find the extensive property of volume and internal energy based on knowing how much mass, I don't need a dot there, how much mass I have tells me the total volume. So if I can look up the specific volume in the tables, lowercase v, knowing how much mass I have, that'll tell me the total volume. And the same thing with the internal energy. So what I've just done here is I said, okay, what am I looking for? All right, well, what tools, relationships, laws do I have that find it? Well, I have table properties, but the properties aren't going to give me total volume or total internal energy. I need an equation that converts the specific volume and the specific internal energy given into the total volume and total internal energy I need. So now I've got expressions, right? And then what I need to then do is find properties to go into these equations, because right now, what have I got? I've got two equations with four unknowns. I know the mass. I don't know these things I'm looking for. I also don't know these specific values that I'm going to need to look up. So what I can do is I can go to the property tables and find the specific values that I need. A simple way to write this is I could say, well, P is equal to 900 kilopascals. Write the things that I know. T is equal to 80 degrees C. Yes, I know they're over here, but this is a good way to get it organized. And what I'm doing is I'm saying, well, based on these two things, I can find the specific volume and the internal energy from the properties, which is what I need to do now. Okay. Now remember, if you look back at your list here, I need to determine the phase. I need to determine the phase before I can record the known properties, because I basically need to know which table, which row do I pull properties from. So I need to determine the phase. And we said for determining the phase, when I've got pressure and temperature, my diagram is going to look like this. You got P, T, and a curve right there. I'm going to draw this on the note so it's a bit bigger. So given, or I'm going to draw it in the PowerPoint slide so it's a bit bigger. Given pressure and temperature is the combination I'm given here. So I have a curve here that looks arbitrarily just kind of like this. And if I go pull then, I'm going to stop share so we can see the charts, tables. So if we go pull then, this is saturated R134A in metric units. What am I given here? I'm given 80 degrees C and 900 kilopascals. So I could come down here to 80 degrees C, which is on the very bottom, and I've got to angle this to get it on here. So at 80 degrees C, I've got 2.63 megapascals, or 2,635 kilopascals. I could use those values, but I'm going to show you what I'm going to do instead. I'm going to go to the next table. This is saturated R134 with pressure, and I'm sorry it's at an angle here. I can't quite get my document camera pointed out to where I can show this to you very well. Remember, what am I given? I'm given 900 kilopascals as my pressure. So if I go down here to a row with 900 kilopascals, notice the column next to it is the saturated temperature. So at 900 kilopascals, the saturated temperature is 35.51. That's what I'm going to record here, right? So at 900 kilopascals, my temperature, my saturated temperature is 35.51, and that's going to be degrees C. I'm just going to write that one time there. Okay. Notice where I'm at. All right, I'm out here at 80, right here. That puts me to the right of the curve. That puts me in the superheated vapor region, right? And notice that if I extend this 80 up here, the pressure is all the way up here at 2.6 megapascals, right? Really, really high. Let's erase that. It was like 2635, I think it was, out here at 80, right? So I can also plot that point. So at this 80, I've got a pressure way up here, but my pressure's down here at 900. That puts me down here. In both cases, if I plot where I'm at relative to this curve, I'm either below the curve or I'm to the right of the curve, both of which would put me in the superheated vapor region. I find it much easier to say, hey, given the pressure, go look up the saturated temperature. Are you beyond the boiling or the saturated temperature? That puts you boiled off. You're over here in the superheated vapor region. That's how I think about it. If you want to look at it and say, well, you know what, at 80 degrees C, I need 2,600 kilopascals to keep it in the liquid phase. I only have 900 kilopascals. That's not enough pressure to keep the molecules squished together in liquid. That's how I think about it when I try to go that way, but it's not natural for me. It's much more natural for me to say at 900, the R134 is going to boil at 35.51. Not something I'm going to memorize because I can go look it up so easily. And I'm over here at 80. So that puts me well beyond that boiling temperature and puts me over here in the superheated vapor region. So what does that mean? Well, it means I've got to go to superheated vapor tables for R134. Right? So R134 superheated vapor tables. This page goes all the way down to 40 megapascals. We're up here at 900 kilopascals, that is zero point 0.9 megapascals. That's this block here. So superheated R134, 0.9 megapascals, that's 900 kilopascals. This column is volume, this column is internal energy, right? And so we see here, yeah, my phone. And we've got a temperature of 80 degrees. So you can see our values right there, right? So I'm going to write those down. Okay. So given 80 degrees C and zero point 0.9 megapascals or 900 kilopascals, the specific volume at that point is 0.028630. Those units are in metric units, meters cubed per kilogram. Those are up at the top of the tables. And then the internal energy value is at that pressure temperature combination is 289.88. And the units in metric, they're going to be kilojoules per kilogram. It's always energy per unit mass. In metric units, that's going to be kilojoules per kilogram. Let's write that a little bit better. 289.88. Always double check those before you set your book aside. And now it's pretty simple, right? Now I just need to multiply these out. So total volume for us is going to be mass, that's going to be my 2 kilograms, times this value here of 0.02863. That's going to be meters cubed per kilogram. And I think I can do that in my head. Some of these I had to break the calculator out, but this one's not too bad. That is 0.0. That's going to be a 5. 8 is 16, plus I'm going to get 1 from this one, so it's going to be 7. This is going to be 12. I'm not going to get another one from that, so it's just a 2, and then it's a 6. I think that's correct. If you get something different, let me know. So there's one answer. Box that one in. That's my V. And then my total internal energy, it's going to be 2 times this guy. It's also going to be a 5. It's going to be a 7. This is going to be a 9. And this is going to be a 7, 6, I believe. Units left are kilojoules, right? Here I've got meters cubed per kilogram times kilograms, that just leaves meters cubed. Same thing here. I've got kilojoules per kilogram times the 2 kilograms up above. That's just going to leave me with kilojoules. There we are. Those are our answers. Okay, I think, yeah, I'm just a few seconds left on this video, so we're gonna stop it here and start another video on that. It's a nice stopping place. Let me know what questions you guys have, okay?